Hi everybody, I thought I'd make this video because some people were asking me about homework 18D, just some of the questions here, so I picked a couple of these questions. And I thought I'd make this video because I can definitely see how these are definitely challenging problems. One of the problems, you kind of have to combine equations to solve for it. The other one, you kind of have to some information is not important. So I've already started drawing my diagram here to just kind of set myself up here, but let's read the question for this one. It says if it takes 10 millijoules, that's what this was supposed to be. This should have been millijoules, not millicoulombs. Sorry about that. But milli stays the same. 1 milli anything is 1 times 10 to the negative 3. So we'll just change that to joules. So we'll change that later. So it goes, so the charge moves from an initial position of 25 centimeters to a final position of negative 25 centimeters in an electric field of negative 20 newtons per coulomb. So what I did is I just kind of drew a diagram here. So we know that the charge moves from an initial position of 25 centimeters. So here's my 0 mark right here because it starts at 25 centimeters. And then goes to negative 25 centimeters. So here's my negative 25 centimeter mark to the left of that. And then it also tells me that there's a negative 2 newtons per coulomb electric field. So negative, that basically means that the electric field is pointing to the left. And then lastly, it tells me that the energy it takes, so the energy it takes is 10 millijoules. And if you do the conversion, I'm going to forego the conversion because that's just converting something. So you're going to get 10 times 10 to the negative 3 joules. So that's the energy it takes, or rather I'll say that that's the potential energy, right? That's going to be my change in electric potential energy. It takes 10 millijoules to move that, from there to there. And it says, what is the charge Q? So, all right, in order to solve this, well, let's see. I know that the charge is moving this much. Let's see, let's do this. So it's moving from here to here. So it's going this way. Like that. That is my, my distance that it travels, right, is going to be from the position of positive 25 centimeters to the position of negative 25 centimeters. So could do this a couple ways. I could just look at my diagram and notice, oh, it's going 50 centimeters. Or I could use the final position, right, minus the initial position. That's the distance traveled, or the displacement. So it's going to be 25 minus negative 25 centimeters, or 50 centimeters. And of course, 50 centimeters converts to 0.5 meters. So I'll just say distance is 0.5 meters. So there's that. Now, that's all well and good. So I got that, this, and this is what's going to help me here. So the other things that I need now are my equations. I know that potential, electric potential, is the amount of electric potential energy per charge. But I also know that my electric potential is the electric field times the distance, right? Those are the two equations from the lecture. If I go back to the lecture here really quickly that we did on Friday, these were the ones I said you would need for your homework. So let's go back. All right. So what I'm going to do is use the, hey, wait a minute. Those are both electric potential energy, so I'm going to set these equal to each other. So if I set those equal to each other, I'll get that the amount of electric potential energy over the charge is going to equal the electric field multiplied by the distance. And now I'm just going to isolate charge. So if I multiply both sides by Q, this cancels with this. And then I get the amount of potential energy, electric potential energy, is E times D times Q. Well, now I'm going to divide both sides by E times D. And then this cancels out with this. And what I'm left over with is that the amount of electric potential energy divided by the electric field multiplied by the distance is equal to the charge. The amount of electric potential energy we got is 10 times 10 to the negative 3 joules. Divided by the electric field, which is negative 20 newtons per coulomb. And then lastly, we got our displacement. Oh, I should be careful. Displacement points to the left, right? So displacement points to the left. So that's going to be displacement points to the left. So it should be this should be my mistake. Sorry, I made a mistake here. The final position is negative 25, and then the initial position is positive 25. So that's still going to be negative 25 minus, so I really just need to put a minus here. So I made a mistake there, I'm sorry. So this is going to be negative 0.5 meters. And then that means this is going to be negative 0.5 down here. And then that's going to give me 10 to the negative 3 divided by negative 20 times 0.5, and I'm getting 0.001 coulombs, because that's the unit of charge there. Or this is, if I convert this, this is also the same thing as 1 millicoulomb. So that's another way to write it. I think that's how the it asks you for it, is for the 1 millicoulomb. So there we go. There's that one. I would say, make sure you draw a diagram. That's where I caught myself here. I made a mistake there. And then also the difficult thing here was that combining these equations here was definitely challenging. So this one is more on what's important and what's not important. So let's see. We got the energy required to bring a charge of negative 8.8 nanocoulombs from far away to 5.5 centimeters. So this is going to end up being the not important part, but I'll just underline it anyway. The point charge Q is 13 millijoules. So I know all this stuff says, what's the potential at the final position of Q? So I look at all this and, oh my gosh, that's crazy. And I give you also all these conversion stuff. That's because another way I'm going to write Q is that it's negative 8.8 in nanocoulomb. If I convert that, it'll end up being times 10 to the negative 9 coulombs. And that's 13 millijoules. So to do the millijoules, so that's my electric potential energy. So that's going to be 13, and then millijoules will convert to times 10 to the negative 3 joules. So again, I'm not going to do the conversions. You should be able to do the conversions just fine. And they're looking for the potential, right? They're looking for delta V. That's just delta V. Or delta VE, I'll say right now. So you might think like, oh crap, I gotta, and then I got distance, I gotta find distance as well, and electric field and all this stuff. But remember, electric potential is equal to the amount of electric potential energy per charge. And I have the potential energy and I have the charge, and I'm looking for delta VE, so I really just need to plug it in here. Divided by the charge, which is negative 8.8 times 10 to the negative 9. If I plug this into my calculator, 13 times 10 to the negative 3 divided by negative 8.8 times 10 to the negative 9. And I get, wow, I'm getting quite a big number. 1.48 and a negative, so negative 1.48, which makes sense. I had a negative right there. So negative 1.48 times 10 to the to the 6th power volts. So that's going to be my volts. But then the other thing I kind of added here is that 1 megavolt. So that a capital M is a megavolt, is equal to 1 times 10 to the 6 volts. So if you do that conversion, another way to write this is to just say negative 1.48 times 10 to the 6 would be a megavolt. So that's another way that you could write this. And I think they rounded to like 1.5 or something like that. So, okay, I hope that helped. And all right, see you guys later. Bye.